All right, it's 2 o'clock. I'd like to welcome everyone to this webinar this afternoon. I'm Adam Green from ATA Engineering, and I also have Chris Ostdeutsch on the line with us today, who's going to help us talk some technical details about some of the new features in STAR-CCM Plus 2020.3. But first, I'd like to go through a couple of slides about who ATA are. We're an employee and small business and engineering consulting group, primarily based in San Diego. We have a very skilled bunch of folk working for the team, including many PhDs and masters. And as you can see down here below, we're very experienced with both professional engineers and the average year's experience of the team. And for those of you who are interested, I don't know if you can see my mouse, this is Chris Ostdeutsch on the right here at the front, who's going to be talking to us in a few minutes. And so which areas of the marketplace do we work in? We primarily work in aerospace and defense, and we do some robotics and controls and some clean entertainment. The others, industrial and mining and consumer products, are fairly small parts of our business, but again, the primary areas are aerospace and defense for the kind of work that we do. And what do we do? What are our services? Well, we're a full engineering consulting group, and we do everything from design, analysis, and test. And we really focus on the test-driven design, and we really basically go from running GVTs on state-of-the-art aircraft right the way through to safety on theme park rides, and even analyzing next-generation rovers. We really do a wide variety of testing. And on top of that, we also are a Siemens Platinum level value-added reseller, which means we sell and support many of the tools that we use in our work. And so it works out very nicely that all of those pieces come together to create a very good environment for our customers. And so that's basically ATA Engineering. And today we're going to talk about STAR-CCM Plus and the 2020.3 release. And Siemens are really throwing a lot of resources into STAR development, and the developments come very fast. Every new release has a lot of important, tangible improvements from the previous ones. And the list this time is fairly lengthy, as you can see. This is just the top 10 out of 29. And interesting to note here is that at the bottom there, you can see that IdeaStorm is a Siemens process for taking ideas from clients and customers and actually getting them into the product. So using the support portals and with Siemens, you can suggest ideas through the IdeaStorm, and they then get assessed and then voted on by Siemens people and other clients and customers to see which ones rise to the top of importance that need work. And so 29 of the features came through that process, which is quite exciting to consider. The voice of the customer is continuously heard. So today, really, because we don't have time to go through all of those, Chris is going to focus on two key features: adjoint-based topology optimization, which is very exciting, and then VOF to Lagrangian transition modeling for really looking at columns of fluid and moving into sprays. So it's pretty exciting stuff, and then we'll be seeing more of that in a minute. But just generally speaking, that the Siemens philosophy with STAR-CCM Plus releases is to look at various facets of where it needs to be improved. And they focus on, in this release, and this is fairly standard, they focus on 4 key areas. And one is focusing on the complexity of not only customer products, but also the physics and getting it right for those products. So they focus on that. And a lot of today's examples are going to show you that application to complex physics. Secondly, they want to automate the process so that instead of doing one simulation, you can do hundreds. And that comes from the interface making it easy to do parametric sweeps to exploration of a design space, right the way through to cloud computing. All of those things make it go much faster. And that's a key vision of Siemens and ATA to support that. And then next, results in hours and not weeks. And when you apply more physics to a problem, often you add more complexity and often a lot more time to run things. And sometimes multi-phase problems can take a lot longer, but a lot of the added features, particularly this year in STAR-CCM Plus with AMR to reduce cell counts, even in multi-phase problems, really has made things go much faster, and they continue to focus on that. And then lastly, the better together mantra is really the idea that Siemens has a huge portfolio of tools in the Simcenter portfolio, and getting STAR to talk to them all very well is an important part of the development process, and that continues to evolve. You know, every release, it has better connectivity to the other tools in the portfolio. And so this next, we actually have a video here, which was recorded by Daryl Schneider, and it really captures 3 minutes of lots of information about the latest release. I'm just going to quickly play this, and then we'll come back to Chris.
Siemens Digital Industry Software provides increased simulation realism with Simcenter STAR-CCM Plus 2020.3, enabling you to accurately model the complexity of today's products and deliver real innovation. Adjoint-based flow topology optimization is an exciting new way to find ideal designs. With an inbuilt constrained optimization method and an end-to-end workflow, you can now leverage this cutting-edge technology to generate highly efficient and often non-intuitive solutions to your design challenges. Improving chemical processes like spray drying or mixing requires accurate modeling of complex physics and chemistry. GPROMS is a powerful modeling environment to simulate such processes. You can now easily use CFD simulations from Simcenter STAR-CCM Plus to calibrate a multi-zonal GPROMS model, improving accuracy and eliminating uncertainty. We've introduced an exciting new hybrid multi-phase capability to more efficiently simulate liquid flows in applications where flow breakup is present, such as vehicle water management or spray cooling. The VOF to Lagrangian transition model resolves the formation of droplets using a volume of fluid approach. To track these droplets, the model automatically switches to a Lagrangian method, significantly reducing computational expense and simulation turnaround time. High fuel loading in internal combustion engines may cause undesired liquid films to form on surfaces. You can now model this phenomenon with Simcenter STAR-CCM Plus in-cylinder solution. This means better understanding of the performance impacts of high fuel loading, including emissions and pool fires, and in the end leads to better combustion system design. Simcenter STAR-CCM Plus 2020.3 also introduces the mixture multi-phase large-scale interface model, a new approach to simulate free surface flows with droplets or bubbles for applications like gear lubrication. This approach removes the need to resolve all relevant scales in the mesh, bringing faster and more accurate answers. The new scale-resolving hybrid turbulence model helps capture more small-scale turbulent structures in an unsteady RANS simulation. This means, for example, increased fidelity of your transient aerodynamics simulations without additional computational cost. Simcenter STAR-CCM Plus 2020.3 makes it even easier to solve your complex design challenges and engineer real innovation into your products. For more information, visit our product website.
So that video pretty nicely sums up a lot of the new features in 2020.3. I especially like the chemical model earlier of the cyclone, where they actually included the guy walking into the scene, which was in the STAR model, which is quite an interesting thing to do to make it look more real. But with that, I am going to just summarize where we are in terms of the two things for today. And basically, we're going to look at Adjoint topology-based optimization and the VOF to Lagrangian transition. And so Chris has been working on a couple of projects for both of those topics. And so with that, I'm going to pass the ball to Chris.
All right, thank you, Adam. I'll just get my screen set up. Can everybody see my slides?
Yep.
Great. Okay. Well, thank you. My name is Chris Stoyich, and I'm just going to talk a little bit more in depth about what Adam had started presenting. As Adam mentioned, there were major, several new feature additions in STAR-CCM 2020.3, and this is a short list of those, and I'll be talking about an even shorter list. The adjoint topology optimization and the hybrid multiphase VOF to Lagrangian resolved transition model. I won't go into the rest of these because I think you got an idea of what they are based on Adam's presentation earlier. But if you are interested, the full list is available on the support center at this link here. You can just actually search for feature additions in STAR-CCM 2020.3 and it'll pop up. So I'll first talk about the adjoint topology optimization. So topology optimization methods generate geometry to maximize some engineering objective. In this case, it places solid material into the flow domain to create the flow path geometry that produces the desired result. In the case of the adjoint topology optimization method, it uses adjoint-based gradients to derive towards an optimal solution. So as I'm showing here on the right, this kind of illustrates how that works. I've just got it on two axes with one parameter on the x-axis and parameter 2 on the y-axis, but really this is the number of kind of degrees of freedom in the model. And so the method says, okay, we're driving towards some optimal design, and we've got this initial design. We calculate the gradient that we think is pointing towards the optimal design, and based on that gradient, we change the model. That gives us a first iteration, which is not yet at the optimal design. So we do this again, calculate the adjoint-based gradient once more, go to iteration 2, and so on until we reach something close to the optimal design. So some of the potential benefits of adjoint-based optimization is one, it can improve flow efficiency by removing wasteful flow features. This model also doesn't only work with flow, but also thermal physics within the solid. So in cases where that's important, it can improve thermal efficiency within your solid. It reduces innovation cycle time. Instead of an analyst making these decisions, the computer is just driving towards the optimal design. And one big one is it does not need to be parametric. So a lot of other optimization schemes, you need to parameterize your device before running through the optimization algorithm. This doesn't need to be parameterized. So I'm going to give an example here. The one that we've chosen is actually was proposed and did a lot of the work was done by my colleague Tyler Pierce, and it is a rocket engine pintle injector. So this pintle injector, which I'm showing on the right here, introduces rocket fuel, in this case RP1, and liquid oxidizer at the same injection point in the combustion chamber. So kind of shown here, the fuel will come through this pathway and it gets introduced. This is a 2D picture, but it gets introduced as like kind of an annular flow around this cylinder, which through the center the LOX flows, and they kind of combine at the orifice. So there's this annular fuel flow around this cylindrical oxidizer flow. And then they get mixed in the combustion chamber, and combustion happens. Combustion efficiency increases with the level of mixing between the fuel and the oxidizer. And the fuel path geometry of this flow path, or this fuel flow path, can dictate the flow condition at this fuel orifice here where it exits. So a more turbulent flow can enhance mixing and therefore can increase combustion efficiency. And so what we're going to do is use adjoint topology optimization to optimize the flow path and increase fuel turbulence before it gets combined with the oxidizer. So here's kind of a little cartoon of what we'll be doing. On the right here is our representation of that fuel pathway. This is just kind of a, well, it's 3D, but it's kind of just a thin 2D section of what would be occurring around the entire liquid oxidizer kind of cylinder flow path. But the point is, this orange part is the initial shape that we're proposing, and we're going to use the optimizer to give us an optimized shape. And with the objective of maximizing the turbulent kinetic energy at this exit plane where it would combine with the LOX. The models that we're using are the steady coupled flow solver using Mentor SST turbulence model, the Adjoint solver, of course, topology optimization, and we're also using AMR to resolve, sorry, this says VOF interface, but to resolve the interface between the flow path and the boundaries that are being optimized. The mesh is small, it's 120,000 cells. And so I was able to run this very quickly, 2 hours on my local computer on 8 cores to run 60 of these optimization iterations. And so in the next slide, I'll show you a video of what that optimization cycle looked like. On the left is the updated geometry. This is kind of a representation of where material is being added to form that flow path. On the upper right is a plot of the turbulent kinetic energy at the exit plane as a function of the optimization design iteration. And then on the lower right is just a contour plot of the turbulent kinetic energy contours at the exit plane. And you can see after 60 iterations, we kind of reached an objective asymptote where, you know, further changes didn't really improve the design too much. So in our final design, you can see, as compared with the original design, that excess volume was removed from the flow path, and the turbulent kinetic energy at the exit was maximized. So this is kind of a funny shape that was spit out the other end of this optimizer. And, you know, a manufacturing engineer would say maybe, hey, how do you manufacture this? But with additive manufacturing, this can actually be manufactured as is. And so this is an interesting example to look at, because of the increased use of AM in kind of rocket engine development. Otherwise, you know, an engineer could just use this as a guide to offer suggestions for a similar design that could be manufactured using conventional approaches. And so are there any questions? Also, I can wait till the end to take questions.
Chris, this is Adam. I have a question. Could you go back to that previous slide?
Yeah.
When you look at the picture on the left of the three there, and you've got the zone of dark blue where I guess that means there's no flow. Why would that stay in the model? Why wouldn't the surfaces be shrunk closer to where the flow is actually moving?
What I'd guess, Adam, is that while that zone might not be contributing to, you know, optimizing the objective, any change in that zone might not make a you know, might not make a big change to the objective. So
Right.
I'm guessing that maybe that would be removed with further iterations as we, you know, kind of chug on the problem a little bit more. But I don't think you see that the objective has asymptoted, so I don't think any further changes would really I think these changes would occur slowly.
Right. Thank you.
And I have a quick question too. How does this optimizer compare to maybe the other optimizers available in STAR-CCM Plus or HEEDS? Like, when would you choose one or the other?
So as compared with HEEDS, in HEEDS you need to parameterize your problem first. And you wouldn't be able to obtain a shape like this if you had to parameterize the model. It would be like, okay, what's the width of this going to be, and maybe what the width of this is going to be, and the length of this. You wouldn't get such a unique solution if you're parameterizing everything. So you have those constraints with HEEDS. There's another shape optimizer within STAR-CCM Plus where it kind of moves the boundary, but that's also kind of constrained by the original shape of the geometry, whereas this is driven by those adjoint computed gradients to remove everything that's unnecessary, or to remove or to place material in locations which would optimize the flow path.
Cool, thank you.
Thanks, Chris.
All right, well, thank you guys. So now I'm just going to talk about the volume of fluids to Lagrangian resolved transition. So volume of fluids, or VOF, and Lagrangian multiphase, or LMP, are two different approaches to multiphase modeling, and each has their distinct strengths. VOF, for instance, is an Eulerian approach, and in this case, you have to resolve the interface between phases spatially on the grid. So that's kind of demonstrated on the right here with this blue blob that's labeled VOF resolved. This is good for flows of immiscible fluids and free surfaces. So as Adam showed in his video that he played, it can be used, it's used heavily in the marine industry, where you've got, some boat floating on top of the surface of the water. LMP is a Lagrangian approach, which models groups of particles as parcel. The parcel equations of motion move, or the parcels move subject to fluid loads entering the equations of motion, and they do not need to be resolved by the grid. So as I'm showing here on the right, we've got these LMP parcels. They are much smaller than the size of the grid, but it doesn't matter because we're just following the trajectory of those parcels. This is good for dispersed flows where you've got a small number of secondary phase particles dispersed in the Eulerian primary phase. So that's great, but it's not uncommon for a flow domain to include, both free surface flows and dispersed flows. I'm kind of showing that in this picture on the right, where we've got a picture of the surface of the ocean, and it's got some waves in it. But as the wave crests, these droplets or ocean spray comes off the wave crest, and those are more well suited to be modeled by the Lagrangian approach. So if we could use a hybrid model incorporating both the volume of fluids and Lagrangian approaches, that exploits the strengths of each model. And so STAR-CCM Plus 2020.3 includes a transition model called the VOF to LMP resolved transition model to identify when and how to properly convert between VOF and LMP. And so basically what this transition model does is tracks the size of fluid blobs in the volume of fluids model. And when the blob diameter drops below some threshold, the blob is marked for Lagrangian transition. So I'm just showing on the right here with that droplet picture, we've got some portion of that flow is suitable for VOF, but then we've got these blobs kind of coming off the top, and those would be candidates for Lagrangian transition. In the case where the blob volume ratio is close to 1, the resulting droplet has roughly the same size and velocity as the blob. So you'd have this VOF blob, which would just pretty much be converted straight into a Lagrangian droplet that would be very similar to it in terms of velocity and shape. Additionally, when using this, it's advised to use AMR to resolve the VOF surface and the blobs during the portion where they're being tracked. And then, as they transition to a Lagrangian droplet, the additional mesh thrown at the blobs to resolve them are coarsened. So the example that I'm going to show here is just a simple water fountain kind of described on the right. The models used are the implicit unsteady segregated solver. Again, I'm using Mentor SST, activated volume of fluids, LMP, and the transition model. I've specified a blob size of 2.45 millimeters, which is roughly the size of a cell that I'm using to resolve the jet. And so what my intent is that when the blob becomes unresolvable by the Eulerian mesh, it then gets transitioned to a Lagrangian particle. And again, as I mentioned in the previous slide, I'm using AMR. The mesh is still not that big, 661,000 cells. And then, as you'll see in the next slide, I also had some fun with screenplay and advanced rendering in the post-processing to make this look more impressive. So here we go. We've got this nice little grove of trees growing around this magical kind of spring here. And you can see we've got this water fountain shooting up. There's some instability, but as it kind of breaks apart at the top, you can see the Lagrangian particles falling off of it. One kind of modeling mistake that I made is the particles just seem to be bouncing along the ground, and that is clearly not what water droplets would do. So that was a boundary condition issue that I should have set on my part, saying that they would stick. And anyway, that's my last slide. I can leave this video up because I think it's fun to watch, but I can take any questions if anybody has any.
Chris, this is Adam again. When you've got the particles, when they become a Lagrangian particle, like in this case, if they hit the floor and puddled, could they go back the other way? Could they go back to a VOF model?
Yes, yeah, they can. You can also have them go into maybe a fluid film model, if that might be more appropriate, because then they would, unless they were pooling in some sort of divot that had, a large amount of thickness, maybe a more appropriate way would be just have a little thin puddle represented by the fluid film model.
So this could be used for kind of a spray painting model.
Yeah, in a previous simulation that I've seen, I guess I'm not an expert on spray painting, but I think that a previous simulation that I've seen the spray paint is, kind of atomized as it's exiting the nozzle. So it'd already be, I don't think there would ever be a time where it'd be appropriate to use volume of fluids. I think it would be just directly
Right.
to Lagrangian and
Just
then
particles out of the gate. Yeah. Thank you.
welcome.
All right. It looks like Chris must have covered it so well. If anyone's got any questions, please shout now. And if not, I say thank you for attending, everybody. We appreciate it, and we hope you enjoyed the presentation. And we will now close the meeting. Thanks a lot, everybody. Bye-bye.